Students, and welcome to the lesson on the product rule and the quotient rule. And let's start right off the bat here. I've got an definition here that gives you the derivative of the product of two functions. Now, if you recall from other lessons, for example, the sum of two functions, the derivative of the sum is also the sum of the derivative. And that is not the case when it comes to the product. Okay, so if you have a product, then you take the derivative of it, you actually get this expression here. Okay? And the way we can look at this is saying the derivative of the first part times the second plus the derivative of the second times the first part. Okay? And in this lesson, I'm actually going to prove this. And if you like doing calculus proofs, and quite frankly, who doesn't? This would be a great example of how one works. And one of the ideas in calculus for doing proofs is just when in doubt, add 0 or multiply by 1. Okay, add 0 or multiply by 1. It's a really silly rule, but it actually works quite well. So first, let's begin with the definition of this derivative right here. Okay. And we're going to use the definition using the difference quotient. So the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x, g of x, the whole thing divided by h. And our goal here is to somehow get this expression, do some algebra to it, to get the derivative of f times g plus the derivative of g times f. And in the next step here, and this is truly a magical step, the first people who were able to figure out this proof added this extra step, and they did it using some combinations of squares and rectangles in order to see it. But for the purpose of what I have here, I'm just going to tell you what this step is. Let's see. So this is a neat little technique that we're just really saying just add 0. Okay, add 0, and you'll see what I mean. If you see in this expression, I've written out the exact same thing, and I've included this part here written in red. But if you look at it carefully, the first term is negative f of x plus hg of x. The second term is positive f of x plus hg of x. So if you look at the red text here, you can see that that is essentially 0. Okay, so all I've really done here is added 0, but the trick is to select the right version of 0. And again, if you were asked to do this proof on your own for the first time, I think you might struggle for a very, very long time, maybe many days, before you're able to see this part. Okay. But I want to show you this so that we can illustrate how these rules come about, and that there is actually a reason behind all of this. It's not just something that's entirely made up. Okay. And then after this, what you can do is really see this as two separate parts. We're just going to group it in this way. Okay. So I'm putting some square brackets around here to help you kind of see the different parts that we're going to use. Right? And we're going to take each of these individual parts. We're going to apply limits of sums, okay, in order to see how all of this comes together. Okay. So all I've done here is just separated this entire fraction here into two different parts, and this is saying that there's this rule we learned way back in chapter 1 that says the limit of a sum is the same thing as the sum of the two limits. Okay? And then from here we'll work on these pieces a little bit in order to simplify it down a little bit further. But from the first part here, we're going to factor out this term, okay? And then in the second part, we're going to factor out this term, the g of x. Okay, so, and there you have it. We pulled out f of x plus h, and then what we have remaining is g of x plus h minus g of x. That's the inside term here. Over here we factor out a g of x, and you have f of x plus h minus f of x. And then let's look at some other things that's going on here. If you look at, say, just the right term here, you see here that g of x is constant with respect to h, because g of x does not depend on h at all. And so g of x here, g of x is constant with respect to h, okay, since it doesn't really have any influence, or is not influenced by h. Because in other words, in this case, h is really the variable, and x is kind of a constant. Over here, we have this red term here. This is not a variable. This is dependent on h, but we can apply over in this section here. We can apply the product of limits. Okay. So let's see what happens in this next step here. Alright, so we're essentially taking this f of x plus h out in the front, taking the limit as that approaches 0 of x plus h, times the limit of what remains in here, which is g of x plus h minus g of x over h. Over here, because g of x is a constant, we can just pull that out in the front. H is the variable, so g of x does not depend on h. G of x is the constant, so we can pull that out in the front, and then multiply that by the limit of the remaining expression here. Now, if you look at this, well, this right here is just the definition of the derivative. This is just g prime of x. And if you look at this right here, this limit out in the front, we can actually use direct substitution, plug 0 in here for h, and you would get f of x. Okay. Over here, well, plus sign, we get g of x down here. And if you look at this expression, this is just the derivative of f. So then here we get times f prime of x. And there you have it. This is the product rule. And what you've just seen here is the proof of the product rule. Okay? And it's good to do these exercises. If you were to take the AP exam, you're never going to be asked to do a proof, but it is extremely useful to be able to apply the definition of the derivative to complicated statements, and it's also very useful to be able to work with limits and apply and manipulate these limits within reason according to the rules and properties that have been established. Well, thank you for watching. As always, ask for help if you're struggling. Have a wonderful day. In the next video, we'll actually do this example.